The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Any issues with the project so far? Have you gotten your repositories set up and the compiler works and all this? So I'm glad to see a lot of people are getting an early start. In fact, if you haven't, a lot of your other people in the class are getting an early start. So you're behind already. So go there, get the project started, because these performance projects can run for a long time. And in fact, last year, a lot of people were asking, when is my project done? Because a lot of times when you have a project, there's a certain set of, we ask you to implement. One that's implemented, the project is over. But when is a performance project done? And the only answer I can give is when the deadline comes. Because you can always keep doing, you can always shave 10% here, you can get a better data structure, you can keep like kind of tweaking for a long time. And a lot of you will do. And in fact, to give a warning, last year, the performance difference between the best project one versus the worst one, even the worst one got about 50% better than the code we gave. But the best one got 1000x better than the worst one, because they figured out the right data structures, they changed the algorithms, they did some pre-computation, they did a lot of cool stuff. And so there's a lot to get if you do this project right. So just don't be happy if you just got 10%, 50% and say, yeah, I got some performance. Think carefully. There's a lot of room in this project for you to gain. So work hard. I'm not saying this year it's 1000x. I don't know. I haven't exactly seen all the things you can do. But there could be a huge thing you can win. So think through not just small, low-hanging fruit, but there could be interesting things you can do that can have impact. So today, what I'm going to do is talk a little bit about basics of performance engineering, kind of things you guys want to probably know, rules to follow. So to start that, if you look at performance engineering, it can fit into a couple of classes. One is you want to get a maximum out of the compiler you have, the processor you have, the system you have. You don't want them to run inefficiently. So if you look at the matrix multiply example we did in the first class, it's saying, OK, we have a system. We have this very well-known algorithm, well-known piece of code, and we want to get the best out of that thing. How do you go about doing that? That's mainly we focus there. Then when we looked at the bit hacking stuff that Professor Lysason did last time, it's mainly about really changing the algorithms. We basically said, OK, look, if we are thinking about this as bits, there might be fundamental different ways to approach this problem. By doing that, we can actually get really good performance. OK, we'll be doing more of that. Today, we are going to focus on these two middle criteria. What we are going to do is we are going to stay within the spirit of the program that is given. So even though we are going to change the program a little bit, we are not going to fundamentally change what the program does. So the same computations would be done basically on the same data, but what we will do is we will change certain aspects, how it's being done, to gain some performance advantages. So nice thing about this one is you don't have to really understand the algorithm. You don't have to understand a lot of what's going on in what's the implementation. This is more, you can do this as mechanisms above. The unfortunate thing is there's no theory in this type of engineering. There's no something we can prove, here's the optimal you can do, there's something that's nice there. So normally performance programming basically involves that you need to understand everything that's involved in performance. That means all the way from high-level algorithms, every level in the systems, the compiler, the hardware, the disks, all those things can impact performance. So it's normally when you're doing performance, you have to understand everything that contributes. This is very different from a lot of what you guys are used to, which is staying within one layer. You say, okay, this is my layer. I don't care what's underneath. I don't care what's about. I am going to work on that. And the thing that normally comes and bite you is the other layers that you just take for granted. In performance, it's basically going through end to end. That's the normal thing. And normally, if you are an experienced performance engineer, you know when the problems show up. And you can kind of have a basic understanding, here are the kind of places where they have performance problems. And so a good performance, this is where the experience come in. So instead of saying, looking at the code and say, I have no idea what's going on, you can say, let me think about this. This is where normally some things go wrong. And then you have to have the skill to zoom in and identify the problem fast. And most of performance engineering is basically good dose of common sense. So have like kind of a good person who can do very good debugging is you have kind of a built-in algorithm. How do you go about doing something? And a lot of times you know your strengths, the kind of mistakes you make. You look at those things first. And the same way, performance engineering, there has to be kind of a back of your head algorithm. And hopefully, at the end of this class, you're going to develop that. And in this lecture, what I'm trying to do is come up with a set of rules. That's kind of patterns that occur regularly. Mistakes a lot of people make, and that can have a substantial performance impact or performance gain if you do that. If you have done the design patterns lectures in 005, the years you took, you will see some similarities. What you're doing is kind of say, okay, here's a bunch of patterns in there, what we can do. So what I'm doing is I'm following some very interesting set of rules that was developed by this guy named John Bentley. He wrote a book called Programming Pearls, I guess. It's an very old book. It's last published in 1990. Talk about a lot of these small, interesting things you can do to get really good performance. It's out of print. If you look, and this is probably one reason to probably go to library. Probably libraries have this copy, but you can't get it on Amazon or online. So that's unfortunate. But what I'm going to do is I'm going to kind of reiterate and some of these rules modified to suit the current programming practices. So he looked at it and said there are basically two kinds of things you can do. You can modify data. You can modify code. And then went down more into details. If you modify data, you can do three things. You can pay one against other. You can pay by space and gain time. You can pay from time and gain space. And sometimes, if you're lucky, you have a win-win situation. You can get both space and time advantage. So let's go through a couple of those things. So if you play by space for time, there are four things. One, I'm going to go through all these four: data structure augmentation, storing pre-computed results, caching, and lazy evaluation. So what's data structure augmentation? So here, what you want to do is you have a data structure that you keep the data. You want to add some extra information to your data structures that can make the common operations run much quicker. Okay? And when this is good, because what you want to do is adding this information has to have a clear benefit. Calculating this additional information has to be cheap and easy. So you don't want a situation where this information, you spend all this time calculating this additional information, and you're not using it that much, or the use doesn't give you that much advantage. So you have to amortize the cost in here. And then also this keeping that information current can't be too difficult, because sometimes you can add information into a data structure that makes it very hard to make sure that that information is kept up to date. And then you're spending more time and your energy doing that. So the kind of couple of quick examples in here. Something like if you have a single linked list, if you are doing a lot of deletion, it's a very expensive proposition because you might have to walk through the entire list to delete an element. But if you are doing a double linked list, a deletion operation is basically order 1 instead of order n. So suddenly you realize I'm doing a lot of deletions. Suddenly I can say I'm adding this additional information to my linked list. I'm maintaining pointers to both directions, make this one operation run much faster. This is a very classic example of adding additional information. Another one is what we call reference counting. So assume I have an object somewhere, and I want to figure out who points to me. In something like garbage collection, you want to see if anybody points to me. Normal way to do that is look for every other thing, saying, is anybody pointing to that person? You have to walk through every possible object out there to find if anybody is pointing to this object. That's what normal garbage collectors do. But there's something easy, what we call reference counting. That means if each object keep a count on the amount of pointers coming to itself, then to ask that question is very trivial. You look and say, okay, what's my count? If this count is 0, nobody's pointing to me. But of course, every time you point to that object, you have to update the counter. Every time you point away or take away an object that points, so you have to subtract the counter. So you have to keep that information additional. But by doing that, this question about asking whether anybody points to you becomes a very trivial question. So here's a case, you add a little bit more information, and that makes some questions, some things you want to know, trivial and very easy to do. And you have to figure out where the overhead is. So here's one interesting thing. Go a little bit further. One thing you can do is pre-compute results and store it. What you're doing is you want some computation, and instead of every time you want that in recalculating it, you say, okay, look, I'm going to compute them early, and I'm going to store it somewhere, and then every time I want that, I just do a lookup. So when is this going to be useful? So this is, rest of my slides are going to have this kind of form. I'm going to give a problem, tell you when it's going to be useful, and give some examples. First of all, the function you're calculating has to be somewhat expensive. Otherwise, if it is just a simple single operation, lookup is probably too slow to compare. And the function has to be very heavily used, because if you're calling it many, many times, it's worthwhile storing it. Another very important thing is the argument space has to be small. You might be asking for calling the function millions and billions of times, but every time you call, you give different set of arguments. If the arguments are very large, it can be many, many things here. Then it's not easy to store everything. And it might take more time to find all the solutions for all the arguments. So if the arguments has to be small. And of course, a couple of additional things. Results only depends on the arguments. So assume the function results actually look time of day to do the computation. Okay, that doesn't work, because then every time you call the function, you get different results. That doesn't work in that much. And function shouldn't have side effects. What that means is if you call the function, if it is modifying some global variable, global state, okay, then if you keep the call, if you don't call the function, that might not happen. So you want to make sure that this function is something you can not call and give the results, and the state of the system won't change. And another interesting, nice thing to have is function deterministic. That means every time you call the function, you get with the same arguments, you get the same results. So this is a long list. Some of things I will go. So what are the examples? Okay, so instead of me giving all the things I want, you guys also, when I give a prescription like that thing, what kind of things can I do in this way? And that might be helpful. Can anybody come up with an interesting example? Where would I pre-compute and save? Anytime you do dynamic programming. Okay, this is dynamic programming is a very good way. Later we will probably get a little bit into that where you pre-compute and save results. Okay, that's a very sophisticated answer. Good. Any other things you can think of? That's almost a meta answer. There's an entire class of things you can do. Any problem there that you have encountered that you'd rather pre-compute and save? That would be a big win. Operations with? Large primes. Operations with large primes, yes. If you are doing that, especially if this fits into this argument space small part. If the large primes are any large prime, then you might not call it multiple times. So here I want to give you kind of a template. That's what happens here. So what you want to do is, at the initialization time, let me see what I can get. Okay. I get this function initialized. What I do is I pre-compute for all the arguments what the results are, store that. And then every time you apply the function, I just basically, instead of calling the function, I will just look at this table. Okay? So when would this be a bad idea? Yes. So if the argument space is very large, or if you don't call the function that many times, or as you said, it might only call for very small number of arguments where the argument, less than argument space. This might not be a good idea. Okay? So we will go, as we improve, we'll see some other things that actually address that. So here's an interesting way of doing of use case in here. So what I have here is Pascal's triangle. How many people know Pascal's triangle? Okay, good. So I don't have to explain that. So here's a simple computation for Pascal's triangle. So what I'm doing is, in order to calculate this value, I'm calling these two values and adding that. Okay? But the problem is that this will call this, so it kind of called exponentially more and more doing that. So it's an exponential algorithm. However, what I can do in Pascal's triangle is I can basically compute it at the beginning by storing the previous row or previous set of values in here, and then previous row, and every time I'm calling, I just basically have to look up the two elements in the previous row. Try to get my mouse. Okay, I only have to look at the two elements of the previous row. I add it up. I will never have to compute beyond that. So in fact, by just doing this one, I have taken exponential algorithm to basically a linear pass through the data, basically. This actually become a square, because if you have some depth, I have to do I squared. It become a square pass through the data. If I'm looking for n, I don't have to do exponential lookup. Everybody saw this? So this is a nice way, simple way. I'm just doing a simple storing this data. However, in here I have to calculate. I need to know how much maximum of that and calculate, and I just look up. And here the savings is so large. If you calculate a little bit extra, who cares? I'm okay. And another interesting thing is Fibonacci. And again, here, if you do this, keep in the previous value, in here, you're actually changing from exponential algorithm to, in here, basically linear calculation. Okay? So this is almost algorithmic change here. I kind of lied when I said it's just a data structure change, but just the simple data structure change made algorithmic difference. So the other interesting thing you can do is caching. So what that means is, if you have a heavily used function, you can keep some number of previous basically results from calling that function. Okay? This has a lot of caveats. So let's go through this carefully. Again, the function has to be expensive, otherwise it's not worth doing all that work. Functions has to be heavily used, otherwise you are calculating, and if you don't reuse it, it's not worthwhile doing all the work. Here, the argument space can be large, okay, because you are not calculating everything. You can have a very large argument space, and that's okay. And then there's another thing called temporal locality. Anybody knows what temporal locality means? Okay, what's
same arguments are called in the second space.
Yeah, so a lot of times we realize if we go into lot of the caching and stuff like that, we really get into that in hardware when you talk about hardware lecture. So what happens is, we have observed that if I have set of arguments and if I calculate, most of the times I will have the same arguments very quickly, time-wise. So if I calculate something within very short time, I might reuse those arguments again and again. So that's called temporal locality. So caching works when they have very good temporal locality. And then there's two other things we want to do, because we want to have a hash function. That means because you have a lot of arguments from that, we want to get a one value to look up where I store in cache. So I have to have a cache function that's calculatable by arguments. Sometimes if the arguments are too complicated, you might not be able to calculate a good hash function. And the hash function has to be good. What do you mean by a good hash function? Yeah, low collisions. That means it has to be a good distribution. So given most of the arguments, it shouldn't be ending up at the same value again. So you should have a good distribution when you call with different arguments. And finally, results only depend on arguments. That's again, otherwise you have a problem. And a function has no side effects if you are storing this important. And there's another thing called coherence. So what that means is, I keep some pre-calculated values in here. And sometimes if results are only dependent on the arguments, you don't have that much of an issue. But sometimes you might end the situation that the results are dependent on arguments and some other things like the time of the day or whatever. Okay? And if you want full coherent, what you have to make sure is, minute you know that the results might be invalid, I need to understand that, I need to invalidate all the cache. Because suddenly realize, oops, the day change or the user change. So that thing I memorized only works for user A, now it's a user B, that the results are wrong, and I have to get rid of all the results. Or there are some cases where you can say, yeah, a little bit of things I can tolerate. Like, for example, really far-fetched example is something like, if you are looking at a web page on a search, okay? You don't have to go guarantee that all the web pages in the world or whatever is in that search. If you're a little bit late getting a new web page, then you're okay. So you can tolerate sometimes, a lot of times, if you can tolerate these kind of things, you can have huge performance impact. You don't have to be exact. So some of these projects we look at these kind of ideas of tolerating a little bit of slack and getting good performance hit out of that. So here's the kind of code. I put a lot of code in my slides because not I want to explain everything, but since these are online, if you want to figure out what the right template is, you can look at it. I have no idea why this is moving on me. Okay. Okay, here we go. So what you first have to say is, every time you cache a value, you have to know, oops, why is that? I have to know all the arguments and results. I have to store that. And then I am keeping this many pre-computed values in here. And so every time I call with a function with the arguments, first I have to get the hash with those arguments. Because that might be the place. This bucket might be the place I have stored the previously computed same value. And then you say, okay, look, what's stored has the same arguments. If that means I already have that pre-computed, at that point I just return it. I have no issue in there. Otherwise, you have to call the function because I haven't stored it. And then I will go about storing the value because this is I calculated it. I need to store it because the next time I call these arguments, I want to get the same results. And then I return the result. Okay? This is kind of clear how this caching works? Okay, what's a good place for caching versus pre-computing? Any idea what can make a good scenario where actually caching can have a big impact? You have heard a lot of things that have the word cache associated with it. And you can say, okay, what's that means? Web browsing. Okay, your web browser actually does a cache because there's a good probability that if you looked at a page and you might be refreshing that page or you might be looking at that page. So a lot of times what you do is you keep a copy locally and the next time you ask for that, and then if you have local copy, you can give that local copy back. And then of course there's issues about how to make the local copy stale, the coherence issues and stuff like that can get complicated. But that's a situation where actually you can use caching. So finally, in this category, we are going to talk about lazy evaluation. So lazy evaluation means basically, a lot of times you might ask for value, but you might not really need it at that point. Just keep the computation to the side without doing it, and then do the computations only we really, really, really need the result. So basically, this is useful. A lot of times you might try to compute a lot of values, but only a certain of that actually is used. And at that point, you just basically defer the calculation and only use it when it's actually done. And nice part is when the accessing this can be done in a function call. And also results can be calculated kind of incrementally. And also, the arguments or what's needed to calculate the results can be nicely packaged up, so it can be recalculated later. So here what you do here is in pre-computing, this is something like pre-computing, but You don't pre-compute early. You keep at the beginning, nothing is pre-computed. When you only ask to apply a function, then if there's no pre-computed value, you recompute. Otherwise, you just return the value. So if you compare this one, Pascal's triangle, beforehand, I just computed this bunch of values in here and kept it. Okay, assuming, okay, up to PT max, I will have the results in there. But you might not do that. PT max might be very large, and you might be looking only for small Pascal triangles. So instead of doing that, what you can do is you can do this way. You can keep the array for results. Assume everything is normally in C, it gets initialized to 0 if it's a global array. And then what happens is you look at the results. If the results is greater than 0, we are what you're looking at. That means, aha, I have calculated. I have a new value. I just return it. I am happy. Otherwise, I will call Pascal by recalculating values, because I don't have the current result. And once I get it, I will store it. Once I get the value, I will calculate the Pascal, I will store it, and I will return the value. So what that means is this value, the Pascal yx, will be only calculated once fully. And afterward, every other time you lose that, you actually use the previous value. This is very nice. This works both very nicely about pre-computation, but you don't pay that extra overhead. So you are doing the minimal amount of computation. You can never exceed the computation of the normal computation. So if you only ask for Pascal, very small one, that's exactly the work it will do. But it will also reduce this kind of exponential blow up that happens in the normal computation. So this is kind of the, you can have the cake and eat it too in this world. OK, good. So now let's switch from space for time for space. OK? So here, one thing you can do is, if you have huge amount of data, what you can do is you can store the data in some kind of reduced form. And then what you can do is then you can get a big compression of data, basically. And then as you need the data, you have to do some more computation to get the data you want. So what you're doing is you are really reducing the space you need. But now you are paying by time to get access to that data. So this is viable when storage is at a premium. If you look at systems before 1980s, everybody had to do it because storage was a premium. And all the memory and disk space was so complicated, everything got compacted in there. Now, most of your laptop and desktop, you don't care, you have enough space. However, if you got things like embedded devices and things like that, this still becomes an issue. Or if you have a very large data set, it becomes an issue. And what you can do is, by compressing, drastically reduce the data size. And you can do it in different ways. Sometimes you can do it in batch. That means you keep the data compressed, expand it all, and process. Hopefully you have room for that. Or sometimes if you don't have room, you do by streams. That means you're looking at a small amount of data, expand it, work at it, and then either throw it or again compress and put it back in. And hardest thing is if you actually do random access. That means you're random, go to some data, expand, and this that sometimes has some complications. So there are a bunch of packing methods, and some simplest things are use a small data size. So right now you're dealing with 64-bit words. You can say, wait a minute. This data only need 8 bits. Why do I keep storing everything 64-bit if my data maximum can be only 0 to 156? I can use 8 bits. Or I can look at that and I can use small data size. That's something. And a lot of times people realize a lot of data we are storing are just zeros. There are many different data structures. You have huge data structures and most of it is zeros. And eliminating zeros in many instances can get a long way in many data storage. And something like LC77 eliminates repetitions. So a lot of times what you find in data, you have repeated patterns. You can eliminate that. And then, of course, you can go into a lot more complicated heavyweight compression. So to just give you a feel for what compression is like, I found this cute animation, so I will just show it to you. So here is the input stream. What it has is this character LA, and then it has some notion about how much of repetition it has, character O and 03. So what happens if it is just a character? It will get taken in. So these 2 characters go. Now this 2-4 says, from the point I point in here, go 2 inwards and repeat it 4 times. What that means is basically in here, AL get repeated 4 times because that 2-4. So that means instead of having these 4 characters in there, what it had was it had 2 things, and then O get repeated 3 times, and then it get shifted in here. So by having instead of having 10 characters before, we had 2, 3, 4, 5, 6, 7. 7 out of 7 characters you stored information of 10 characters because of repetition. Okay, so this is a very simple scheme that people use to do. It's called LC77 compression algorithm. More complicated thing you can do a lot of times is build an interpreter. What that means is you have some complex data. Instead of storing the data, you have a summary of the data stored. Okay, and then what you can do is you can do this abstract representation. I mean, you already does that. Like for example, your assembler is exactly doing that. What you do is instead of storing all the bits of machine instructions, you install it in abstraction called add register names or something like that in assembly. What that means is you are building a very simple abstraction, which that would be more complex sometimes to store than the actual data. So in here, things like if you look at a Java bytecode, that's a nice interpreter. So instead of storing all these complex instructions, you stored some higher level set of instructions that are bytecodes that are much more compressed, and as you run, you map it into the machine instructions. There are a lot of advantages other than just compressing storage. It's a nice abstraction. You can change it at the high level easily, etc., etc. Okay, so those are something that you can do. You give up one thing for the other, and if you are lucky, you can have the cake and eat it too, which is both you get space and time at the same time. So we looked at it in last lecture sometime, which is BitHack. BitHacks kind of gave you that because instead of having 64-bit word to represent, you got 64 of them into one big stream if you're only representing zeros and ones. And by doing that, you get a lot more compressed storage. Also, now you can operate that entire 64 in parallel. We can generalize it a little bit. So instead of just doing 64 booleans, sometimes you can do in a 64-bit word, you can store 2 32-bit words or 4 16-bit words or 8 8-bit words. Okay? In x86 jargon, this is called MMX SSE extensions. Normally it's called SIMD, a single instruction multiple data, because what you do to that, all the bits are the same thing for every part. So if you're adding, you're doing same add for both of the data. And because of that, you basically get both the compression. Because now instead of 64-bit, you are keeping 2 things or 4 things or 8 things. Also, now you're operating. In the single operation, you can get the same operation happening to all the data. So you're getting both storage and fast operations in here. Of course, if you want only look at one, you have to do a little bit more work. You have to take it out of that data word. So if you're just looking at a lot of individual things, it can be expensive. So when is it viable? You're doing same operations all the data. Okay, if each data you're doing something different, this is not that great. And the items can be stored in contiguous memory. So when you load, you can say I'm getting in a nice one word if I am getting 2 32 bits, so 4 16 bits. So I can do that. And you don't end up picking each operations and doing individual things too much. So if you have to pick each individual elements a lot, then you have to actually now pick apart that word, and that can be multiple operations and expensive. So here's a simple example. This, I think, from after last BitHacks class, this is a little bit, you probably know, can come up with enough examples. Here, what I'm doing is I am doing a battleship board game. So you have to represent the board, and the interesting thing in this board is to know whether that location has something or not. It's empty or full. That's all I need to know. And so normally, if I do this board game, I can have 2 boards in here. Well, what I'm doing is have this overlap calculation, say with the 2 boards, how many things overlap. I can just have each location represented by integer, but then we're only representing one value. It's not good enough. One thing I can do is I can just put each row into 164-bit word, and then instead of doing these 2 loops, I can, in one loop, I can just do the ANDing of each row, and I get the result. Okay? So after the BTAC lecture, this should be kind of trivial. Okay, everybody get it? Anybody have questions so far? Are we all in the same page? Okay, good. There's a lot of blank faces, so I'll start asking more questions or something. Okay, so that's modifying data. Now we're going to modifying code, where you want to change the programs to actually get performance, and that can be done in loops, logic rules, procedures, expressions, and parallelism rules. When we get to parallelism rules, we will actually do a lot more than future lectures, but I just want to actually address some basic stuff now. Bunch of different loop rules. I will go each of them individually. So first of all, why loops? Why do you think loops are so important? Okay, somebody who haven't answered the question. Why is loops so important? Why are we really focused on loops all the time? Anybody want to answer here, this side? Okay.
In terms of maintainability, you as a programmer doesn't want to change more
Yeah, so what he's saying is loops give you nice, simple abstractions. It's easier to maintain instead of having multiple repeated times. Yes, instead of having same thing repeated millions of times, if it is same thing, if I write a loop, it's much more concise representation. That's why I think we do a lot of loops, because it makes programs easier. In fact, assume this world, loops didn't exist. Okay? If loops doesn't exist, that means you are going at each instruction get executed only one time. If you have a 3 gigahertz machine, that requires, even if you do 1 instruction per cycle in 32-bit instruction, you need 12 gigabytes of instructions per second if you only execute 1 instruction once. That means if you have a 100 gigabyte disk full of a program, you go through each instruction, the entire 100 gigabytes in 8 seconds. Okay? Of course, this can never be done. That means you cannot feed 100 gigabytes into the processor in 8 seconds. That won't work because of the disk access time, caches, and all those. Even if it is doable, okay? What that means is the entire reason your Pentium is running at 3 gigahertz and actually showing like it's running at 3 gigahertz is because you are reusing instructions many, many times. You have loops that run millions of times. If you don't have loops, you can use your whatever the beta machine you build in 004, and that's probably the fastest you could get because of this instruction thing. So loops are critical, and loops are what makes our programs run fast. Repeated execution of same instruction again and again and again. Okay? So in the world, in that sense, if you think about this, is unless there are some instructions that run millions of times, okay, you can never keep this ferocious beast's appetite full, because they will always need new instructions. So because of that, looking at loops, if you want to get good performance, just looking at the most important loops, that are inner loops, and just doing only that will probably get you most of the way in many cases. Okay, and basically, I could even say 99% of the program execution time is in 10% of the code, even more than that in many cases. Because otherwise, this first back of the envelope calculator you can do, you realize how much code you need to feed the beast to keep it active otherwise. So first loop of optimization, loop invariant code motion. So normally in a loop, you run millions of times. And if you do the same thing millions of times and get the same results, you're just doing a useless computation. And so here, the key thing is most of the time, the compiler, the good compiler will come help you. So in this class, you're not trying to replace the compiler. We as humans, you won't do the least amount of work. The compiler is great, dumb thing sitting in there. It can do most of the hard work. The key thing is first, try to get the compiler to do the work. Only do things yourself the compiler cannot do. So most of the time, compiler, if we can analyze the code and prove the results are the same in each iteration, it's going to get rid of it. It will do that for you. But there are cases it's not possible. Because sometimes the computation might be too costly. And also, there might be cases the computation is too cheap, but if you hoist it out, you have to keep the result in some n registers. And if you keep too many things in too many registers, that cost might be too expensive. So there might be a case that you might not do, but most of the time it happens because the compiler can't do anything. So here's a good example. I'm doing, I don't know why I did that, but I square root and take exponential of that. Compiler look at that and say functions. Okay, I have no idea what the functions are most of the time. The compiler can't tell what each function does because it's a function call. It can do any arbitrary thing as far as the compiler knows. It say, okay, function call, I don't know what happens inside, so I'm just giving up and I'm just leaving it. But you, on the other hand, knows that a square root function and exponential function doesn't have any what you call the side effects. That means those functions doesn't go change anything else. It just calculates and return the value. You know that this basically calculates the same value again and again, and you can just basically take it out, do it once, happy. So a lot of times, make sure the compiler can do it. If the compiler cannot do, then you have to go and interfere at that point. So here's another interesting thing that compilers cannot do. A lot of times, you are going through this array or data structure, looking for some value. Okay, once you found the value, you say, okay, I found it, I return. Okay? Normally what that means is when you're going through array, you have to test two things. First of all, you have to test whether you found the value, okay, that you are trying to exit. Second, you have to make sure that you don't overrun the data structure. You're not overrunning the array. You have to make sure you're not at the end of the array because you might not, that value might not be in that data the array. If that's the case, you run to end of the array and say, return, I didn't find it. So you do two tests. So one thing you can do is, instead of doing the two tests, at the end of that array, how about if you add the value you are testing for? So you know when you reach to the end, you will always find the value because you add it there. So you know it's there already. So by doing that, you can reduce the test by just looking for the value. Because now when it comes to the end, you don't have to do any more tests because the value you're looking is already there and you found that, you go out. So, but you should be able to add that value to the end of the array. So what you do is, this is your normal test, that what you're doing is if I can get my mouse, you're going through this array, looking for a value. If value I return, otherwise return -1 in here. Now I do two tests. I do this test to make sure that I'm not at the end of the array and I'm taking this one. So if I actually put a while loop, I just can put the two tests next to each other. So this is what you're doing. But instead of doing that, one thing I can do is put that at the end of the array, after all the data that I care about, I can put the value I'm looking for. And then I just only do one test. I check for that value. So if I find the real value in the array, and at that point I'm done, or I ran out of the array, and after I ran out the real data, I just found the value because I myself put it there. And so I had to find it. And the minute I find it, if I realize that's the case, I say, okay, oops, that's the value I put, and I can return it. Here I have done something which is not really good programming practice. Can anybody put you a 005 hat and say, that's bad programming? I modified my input array. I know. That's not that great. I mean, if I did it really well, if I want to make sure, what I should have done is kept the old value at the end and modify, and at the end, restore it back so it looks the pristine thing I got. I mean, if I was really careful, I would have done that. And then my invariant that my input array haven't changed would be hold nicely. Because here I have mucked with my input array. So even though you're doing performance programming, you should still have a good eye for doing good, correct programming and keeping nice program invariants around than mucking with all over the place. So even though we are putting a new hat in here, you should still have the 005 hat, at least partially. What else can we do? A lot of times what we find is we have these loops. And loops has a couple of issues. First of all, you have to keep checking the loop condition. That's expensive. And if the loop body is very small, the compiler doesn't have that much opportunity to do anything useful with the body. Just basically compile it as is. So one thing you want to do is, if the loop bodies are too small and the number of iterations is small, you want to unroll the loop. So in here, instead of doing this calculation again and again, I want to actually do a computation unrolled, and this gives you two things. First of all, I get rid of this test. So I actually won in here. And second, this computation can be done much faster. The compiler can generate this much faster than this one. Do you see why? Can anybody say why this computation would happen much faster than this doing in the loop iteration?
So you don't have to write the final result of the variable until all the numbers have been summed.
So that's one thing. Even the final results in the register, what happens in here? So that's a good observation, but that's not exactly it in here. What's back there?
You don't have to increment I, and you don't have to check for the condition when
Okay, he got 90% of the way there. First of all, here I had to increment I, and I have to check look the loop condition. There's another point in here. The one and right can be run in parallel. In here, I am doing sum equals sum plus AI. So that means I have to calculate a sum plus AI for A1. Once that is done, and when you get the results, only then I can go add the A2. Only then I can add A3. So last time Professor Lysensen said, in our machines you are using, you can issue 6 instructions at every cycle. Okay, what 6 things you can do in here? Nothing. Because you're just waiting, you're twiddling your thumb for the first one to finish to do that. In here, you can say, look, I don't have to add A1, A2. I can just do these things in parallel. At the first cycle, I can add A0 to A1. That's 1 instruction, 2, 3, 2, 4, 5, 3, 6, 7. I can add all those things together as a tree. I can do tree addition instead of one after another. That can happen in one go, and I can get 6 additions done. And then the next instruction, I add the tree, and at the later stages, do not have too much to do, but I can get a lot of parallelism. So the compiler can actually take advantage of that when you unroll that. So that worked very nicely if I have small number of iterations, but if you have large number of iterations, you can still do some stuff. So in here, what you can do is A goes from 1 to n. You can say, look, n, I don't know. I don't know how to unroll for n because I don't know what n is, but I can unroll partially. So here what I can do is say, look, I will, instead of running it n times, I will unroll my loop 4 times. Okay, so I will at least get enough of an unroll in here. The way you can choose that is you unroll enough that the machine can keep busy. It's not just crawling. And then I haven't blown up my code like crazy in here. And of course, you have to clean up at the end. You have to know how many full iterations. So how do you choose how much to unroll? What impacts my number of unrolls? I unroll 4 times. You can get greedy and say, I'm going to unroll 8 times, 16, 32, 64, 128. How should I choose what impacts? Because a lot of times these are not zero-sum games. Some stuff impacts some on the other way. So what should I use normally for my amount of iterations to unroll? Anybody want to take a guess what helps?
Probably the number of instructions that your processor can execute in one cycle.
Okay, so in one sense, you can look at, say, number of instructions I can execute in one cycle. That's a good thing to keep unroll enough to keep the processor busy most of the time. But sometimes you can say, oh, that's hard to figure that one out. I don't know that because I'm at the compiler, I'm at high level. I don't know what happens low level. I'm going to go unroll 1,000 times or whatever. Why shouldn't I unroll huge amount? What happens if I unroll too much? You might? Okay. Define it more closely. What do you mean?
Perhaps there's some exit condition somewhere in the loop.
That's one interesting thing. Assume your number of iterations are not always millions. Sometimes you might iterate 100 times or 200 times. So if you have unrolled 500 times, you will never get to the unroll loop. You end up in this cleanup loop. And so cleanup loop, of course, is not unrolled, and so you're back to your square one. And so a lot of times, if you unroll too much, and if your number of iterations doesn't fit, so you end up in here, that's not good. Other thing is when you unroll, you create this huge amount of instructions now. That instructions might be too much. It might not fit in the cache. It might just overwhelm the memory system. So you have already now created a loop body that doesn't fit in the instruction cache, and that's not good either. So that will limit the unroll. So you have to. So don't get too greedy. Just sometimes these are the things you kind of play with if in the problems you're looking at, and some of it is architecture dependent. Some of them are things like too much unroll where the number of iterations not that high is problem dependent. Another thing you can do, there are many cases if you have two different very same looking loops, you can put them together into one loop, and that gives the reduce all the loop tests and stuff, and also the array access only is done once, so that can give you a benefit in here. Here's an interesting one. Here you have this weird loop that the j loop run from I to j n minus I to n minus I. How can I improve this one? Can anybody tell me what might happen in here? So I have outer loop I goes from 0 to n. Inner loop goes from I to n minus I. What happened? Somebody's getting that. Okay.
The outer loop boundary to n over 2, I think.
Yes. What happens is because this, the loop is at the beginning, you are going from basically 0 to n, and then the inner, the lower bound is going like this, upper bound is going like this. After n over 2, this is n over 2, there's no iterations left. Okay, you are iterating, and after iterate, so you are running the outer loop n over 2 to n with nothing running on the inner loop. And so if you have this kind of funky loops, you can just look at it a little bit carefully and say, wait a minute, that's not useful. So therefore, I can just get rid of these unused iterations, and then instead of iterating to nothing. So that's loop rules. Loops are very important. Also, we can do a lot of interesting logic rules. So first of all, okay, can anybody shout out what each of these things can be done? Square root of x greater than 0. Square of x greater than 0, sorry. X greater than 0. Actually, not x greater than 0, actually, sorry. X not equal to 0. Because square of x greater than 0. Okay? Here's something your compiler probably doesn't know what the transformation. We can do that. How about the next one? How can I improve the next one? Square root of basically I'm looking at the distance between x and y and AB. So eliminate the square root. It doesn't help anything except do too much computation. Okay, next one. Yeah, I can basically multiply and then take a 1 log in here. Final one. 1. Okay, and then you should go and find that program who wrote that. But believe me, you will find this kind of code sitting in somewhere because you didn't think through. You just start writing, and suddenly you have this kind of nice axiom. So when you do that, this is something compiler can't do. Look for these kind of patterns. That was a stupid mistake, but a lot of other things are things that a compiler cannot do, but you know more math than the compiler does. Okay? And other interesting thing in here is if you are looking something like a monotonically increasing function, okay, let me look at this carefully, because okay, this is very similar to what we talked before with the Sentinel ending. So one thing you can do is I can put the cutoff at the end, and then I don't have to check both the bounds and end. Basically, this is iterating through something. Basically, this is the Sentinel check we did done a little bit differently. Okay? And here's another interesting thing: reordering test. So what can you do here? What do I do here? Here, what I'm looking at is I am looking at two different circles, see whether they are overlapping. They are collision. There's collision in here. This is an expensive test because I had to do square root of some something, get a square root, and check whether it's less than or equal to radius. So here's what I have to do. How can I make this faster? What's the intuition in here? So assume I have this bunch of balls running around in my graphics program. I want to make sure that the balls haven't collided. They are actually moving with no collision with other balls. And I am doing this test. What's a good intuition in here? So he is getting there, because most of the time what happens is, if you are looking at two balls collision, most times these balls are farther apart. And if you just found the square around the ball, testing these two squares are colliding is very cheap. Okay? And then if the squares are overlapping, then and only then you might want to check whether actually the balls are overlapping. Okay, and by doing this square test, you can instead of doing very expensive operations in here, you can basically do some very simple thing. In fact, I have even reduced it more by just first doing the x side, and then if the x is farther apart, I don't even have to check for y. And only if those two checks fail, that I realize, look, the square might be in now there's a good chance it's actually colliding, and there's a really good chance most of the tests will be, after doing the first two things, will be done. You never have to go to these very expensive operations. So here's something you have to have a little bit of intuition on what's going on out there in the problem, and use that intuition to look like more work. But in reality, really reduce your amount of work you have to do, because the test is very expensive. Okay, here what I have done is, okay, this is another little bit of a contrived example. What I want to do is assume I have basically a 4-bit word in here, okay? And I am checking, this should be 8, I think so I have 8-bit word in here. Okay, I am checking whether the 8-bit word is a palindrome. So the way I check the word is a palindrome is, first of all, I set up some bits in here, bit masks. Okay, and I have a bit mask for the two end. I said, okay, if these two are same, then go these two same, these two same, these two same. I just kind of go down the bit mask. Do everybody see how this works? And then in these two, and I kind of shift my bit mask to the side. These two. Basically shift in there. So I'm checking the most two end bits are the same, the next two bits are the same, next two bits are the same, going up to down that. Okay, so this is, every time I do that, I have to actually set this bit mask, do these operations and stuff like that. Assume I'm checking whether my characters are palindrome for huge amount of characters. If I call this a lot of times, what can I do? kind of the out-of-the-box thinking. So the one hint is, if I'm only looking for characters, how many different characters are there? Yeah, because all the characters in everything I look up, I have 8 bits, 2 to the 8. What's 2 to the 8? What's 2 to the 8? Okay, so you have 256 possibilities in here. Okay, so I'm doing this to do 256. Why don't I pre-compute and store? So that if I just calculate for 256 different possibilities, is it a palindrome or not? I just store a bit for each of them, saying it's a palindrome or not. And then my palindrome test is very simple. I just look up my lookup table and say, hey, wait, is it a palindrome? No. Yes, no, done. So if I'm doing this computation a lot of times, I suddenly realize I can pre-compute. This is the kind of things we did before. I am very safe. I can do that. So sometimes you have these programs that has very complicated control structures. But when you look at this here, you realize this if V is used multiple times in here. There's S1, if V S2, else S3, S4 again, if V S5. And so there are a lot of conditions going on in here. In something like that, you can sometimes look at that and say like, okay, look, I am going to, because my conditions are simple, in here I will do one. I just do that one, and I will create the path depending on what the Boolean expressions are. And even if you have 2 or 3 conditions, you can create a couple of paths depending on that. So I'm replicating some stuff, like S1 is in both, S4 is in both. So I have expanded my code a lot. But now, instead of having this spaghetti code that my compiler and my architecture is going to stop all the time, because branch prediction and stuff, as Professor Lysason pointed out, can have issues, I created this nice single branch, lot of code to execute, lot of chances for my compiler to do a lot of optimizations. I can set things like that. And compiler can do it most of the time, and sometimes you might want to help the compiler. Procedure rules. So one interesting thing is, a lot of times when you have lot of small procedure calls, it does a couple of things. Okay, let me ask you, what's the problem with having a lot of small procedure calls? You call a lot of small methods all over the place. What's the problem with small methods? Context switch, yes, because every time you do a method call, you have to basically go change everything in my registers, put it back in memory, stack, and then go do that. I have a basically calling context is the expensive part. Okay, so if I'm doing a very small thing, your calling context might have a lot more overhead than actually what the procedure does, a method does. What else? What's a more subtle thing that can happen? So if you're thinking more, I'm a compiler guy, so I think like compilers. What would the compiler do at this point? Compiler can't say, oops, barrier. I have no idea what's happening in here. I have to treat this as a just big stop. I will do bunch of things above that. I will do some bunch of things below that, but I can't go through that kind of thing in here. So compiler basically treats that as this, like, I can't touch that barrier. And that means the amount of stuff that the compiler can do is really reduced. So one way to do that is basically inline. In a max function, it's pretty simple to inline. Basically, you can define a macro that the C front end will go and inline for you. So this is simple. Or you can define inline method in here and put it in the same file, and then we'll tell the compiler, look, go and try to inline this thing. And by doing that, we are forcing the compiler or telling it the ability that inline, and then not only you're getting rid of the overhead of the method calls, but also you are letting the compiler a lot more opportunity to go and do something interesting. So here's something you will find in many streaming type programs. What you do is you run through a loop, reading through a bunch of data, do some processing, and writing it back. And then you want to get the data you wrote back, read it again, do some processing, and write it back. The problem in this one is the first loop iterates through all data. So by the time I'm done with the first loop, I have written all the data, and the thing I wrote early is probably all the way down in my cache hierarchy. Because I wrote huge amount, it can't sit in my cache, so it goes down, 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 and the next guy has to read it all the way from bottom up. So coroutines means, instead of doing that, what you can do is run for a small amount of data. So you don't run the entire data set, run a small amount of data, write it into a buffer in the middle that we know sit in the cache, and then this guy picks up this buffer and finish it up and write it back. So by keeping the data in the buffer, so what I have done is between these two, I actually had some nice locality. I can keep the data up. So as we go into memory systems and stuff like that, these kind of patterns come up a lot. Tail recursion elimination. So here, there are many functions that the last thing you do is call itself. Okay? This is pretty expensive because what normally happens is when you call a function, you have set up a calling context, you do all this context switch overhead, put things into the stack and go, but you don't need to keep in stack because you are basically done with the previous guy. You are just calling just to go create another stack. In a lot of these cases, you can reformulate the problem into a nice loop that has no function calls. So in here, when you're doing factorial, you can actually formulate the factorial in a way that you don't have to do a function call. So a lot of times, if you end up in a situation that the last thing you do in some part is the call itself, and if you're not doing anything afterwards, you can always end up in a situation where you don't have to do that. You can actually convert it into more of a loop. And by doing this, I got rid of all my calling overhead and stuff like that. I'm just running a nice tight loop. Okay? So this is so if you have patterns that look like that, you can think, okay, look, this is nice. I thought through as a recursive way. I got this there, but now can I transform it to more of an iterative way of executing? In many cases, you will find a way of doing that. Okay. Then there are a bunch of expression rules. So a lot of times you have these computations that if you think carefully, you can let the preprocessor do. So in something like calculate something like that, if I know what R's are, stuff like that, I can just put it in as constants, and voila, I don't even have to pay any cost to compute that because by the time it's compiled, all the computation is done. And this is there are a lot of good cases you can just get rid of work by giving it to the preprocessor. What am I looking at in here? And I'm just calling sin A and sin A twice in here, and then sin A squared. I just basically, the compiler probably won't know that the sin A every time will give you the same number if given the same input. It's a function. I think the compiler doesn't know that. And this is something you probably have to do for the compiler, especially when you know the function has no side effects. This is a little bit more funkier. So assume I do two similar computations. You might want to do them together as a single computation that gives the compiler more opportunity. But that means you have to rewrite a function like a sine, cosine as a one function. This is a little bit of funky thing that in his list of interesting things to do. But I put it there because there might be cases you might find this interesting. Like if you're taking min and max, it might be instead of calling min and max separately, you might be able to call it together. So the last set of rules is parallelism rules. Of course, we are going to visit parallelism like crazy in this class. But today, we will just go through some very high-level stuff to give you a little bit of feel for what can be done. So I have this rule, this program. So what's wrong with this program? Why would this program run very slow? Can anybody tell me? Why can't in this program, I can't use the full utilization of my machine? The problem with this program is every iteration, until this condition is calculated, I can't start calculating this. And so every iteration I have to wait till this is finished, condition calculated and resolved, and you calculate that. And once that's done, you go to the next iteration, go to the next iteration. So by doing this, I can't do too much work. On the other hand, if I can unroll the loop like 2 times and have 2 different conditions, now I can do this condition and these conditions, and these 2 can done in parallel, and when these 2 get resolved, I can do these 2 operations. So instead of doing X max, I am updating 2 different variables, and at the end, I can resolve that. So what I'm doing is I'm calculating 2 things in there, and I go the 4 things, whatever, to keep the machine busy, and each of them can be calculated independently. Okay, so I can get parallelism, and at the end of the day, I can do that. It will help when I'm summing something or whatever. Do you see this? So to get the 6 instruction issued at a time, something like that will give you more abilities because there's more things that can run in parallel. So most of the time, it will be good to see whether you can eliminate these kind of chains. Like here, Xmax is a chain, because Xmax, until the previous is calculated, I can't calculate the next one until that. So I have this chain that until this is calculated, I can't do this. Until this is done, I can't do the next iteration. So Xmax is kind of keeping me very sequential. By doing that, I have 2 things I can calculate. So the other interesting things is if you are doing through this kind of data structure, linked list, sometimes if you have ability to bypass, have another pointer that points a couple of things ahead, then I can keep multiple of them going on. So I can do, instead of waiting for the next one, I can basically switch 2 elements, do that, switch the next one, so I can get some parallelism in here. So I can do things like that. So to get some basic parallel performance going on. And this is basically kind of a little bit of data structure augmentation. You add additional data, make it run faster. And you want to get all your loops vectorized. That means you want to run things like SIMD instruction. If you are using 32 bits, you want to put a couple of them together, run in one SIMD unit. But I don't want any of you guys to go write assembly to do this. It's going to be a big pain to write all the SIMD assembly. We are not talking about assembly, but most of the compiler, like the Intel compiler, is somewhat good at doing it. So what this means is you have to kind of really nudge the compiler, look at a bunch of compiler flags to get the compiler to do it. Sometimes it's when we go more into, we'll figure out how we can do it, looking at giving the right flags to compiler, sometimes changing the program a little bit, that makes it easier for the compiler. So sometimes it's wrestling with the compiler. It's much more easier, believe me, than trying to do it by your hand yourself. By doing that, you can get some interesting performance. And we will talk a lot more about this coarse-grained parallelism, and we have end of the bunch of lectures on that, trying to figure out how to get multi-cores, each core do something parallel, and get all your 12 cores in the machine working for you at a given time than only one guy. And so here's an interesting situation. So I have this problem here. Can I run this parallelly? So what I'm doing is I'm doing these 2 loops, and I am adding adding all the elements of an array to total. Is this parallel? Can I run anything or any of these things parallel? Somebody says yes, no, whatever. What do you think? Take a stand. How many things? Okay, what do you think? Somebody says yes, good. Yes takers, no takers? Yes, everybody says yes. As it is parallel. But look at here, what happens is previous total is needed to calculate the next total. So how can I run this parallel? Okay, so she's somewhat onto it. So let me show you what we can do. One thing you can do is, instead of calculating one total for each basically column, you can calculate its own total. Okay, so what happens is, so for this is I is row, j is column. So for each row, so each row gets a different total, temp total. And so what that means is you can calculate all the column totals separately. You can total all the columns and then total up those values to get the full total. So totaling up columns can be done parallel, because now all of these things can be run parallel, because it's totaling up multiple different values. So it's kind of what she said, but you do it for each row separately. And so here's something, you made the program a little bit more complicated. Actually, if you run it sequentially, it will run a little bit slower, but at the end of the day, you actually get the program parallelizable. So a lot of times when you're parallelizing, is to also looking at the algorithm, little bit changes to the program that at the beginning might look like I'm slowing down the program, but ending up getting good parallel performance. So a lot of parallelism looks like this. So here's the entire list of things we talked about. It's out there, so you can go look at them and see whether you understand them better. And I'm leaving you with this example that I'm not going to have time to go through, which is my programming of a traveling salesman problem. So what you're doing is you are looking at a way for a salesman to travel through all the cities with the minimum cost. Of course, the shortest thing is exponential algorithm, so you don't do that. There's a good heuristic, that the greedy heuristic. Every time you go to a city, you go to the cheapest city that's not visited, and you just jump around. And that seemed to be a pretty good heuristic. And so I coded this up, and I'll go to the end, and then just finish it up. Oops, I went too far. Let me. So what I did was I have 8 different stages, basically. Each stage I did some changes, and at the end I got this program to run about 5 times faster than from where I started. So you will see at each stage what I did. So this is basically out of the menu of things I showed you. I found instance I can do. And then I can, in this program, I got 5 times faster. This is more normal than the 300x fast I got in matrix multiply, and that's a little bit of extreme case. But enjoy looking at this code.